Welcome back. Now, last video, we saw how to write a function as a power series representation. And uh, oftentimes we use geometric series to refer the function to a geometric series. In this problem, the next example that we are going to do is find a power series representation of x cube over x plus 2. In fact, we are going to use the information, the sigma representation that we got for 1 over x plus 2, which was a previous example. So that is the one that we will be using in this problem because we already did that in the previous example. So write x cube over x plus 2 as x cube times 1 over x plus 2. So from the previous example, we can write this as x cube times sigma. So I'm writing the sigma representation for this geometric series, which we got 1 over x plus 2. We got that as negative 1 to the power n, x to the power n over 2 to the power n plus 1. We got this in the earlier problem. That is the representation of 1 over x plus 2. We are going to substitute that over here. So it is equal to sigma negative 1 to the power n x to the power n over 2 to the power n plus 1, n varying from 0 through infinity. So this part is from the previous problem. Previous example. So if I collect all, we also know that when it converges. So then we can actually distribute, or we can actually take this x cube along with the x over here. So it is sigma x cube over x plus 2 equal to sigma n varying from 0 through infinity negative 1 to the power n. You already have x to the power n there. And then you're going to also take x cube, which is outside the sigma sign, inside of sigma, divided by 2 to the power n plus 1. So which is sigma n varying from 0 through infinity, negative 1 to the power n, x to the power n plus 3 divided by 2 to the power n plus 1. If you expand by giving successive values for n, starting from 0, then you'll get to the power 0, then you will have x cube divided by 2, then we will have minus 1/4 x to the power 4, then plus 1/8 x to the power 5. So it alternates in sign. Then this is how we write. We should always tell where it converges. So it converges when the common ratio is less than 1. So it is not very much different from the previous problem. So the common ratio for the previous problem was absolute negative x by 2 should be less than 1. Common ratio is negative x by 2, which means absolute x is less than 2. So in case they ask you for the interval of convergence, you would say it is exactly similar to the previous, which is negative 2 to 2. Next concept is very useful, differentiation and integration of power series. So the following theorem gives a method for term by term differentiation and integration. Theorem 2. If the power series sigma n varying from 0 through infinity c sub n x minus a to the power n has radius of convergence or more than 0, then the function f defined by f of x equal to c0 plus c1 x minus a plus C2x minus a the whole square in the expanded form, in the sigma form, which is equal to C sub n, sigma C sub n x minus a to the power n varying from 0 to infinity, is differentiable and therefore it is continuous on the interval given by the radius of convergence r, a minus r to a plus r, and first one, the derivative f prime x is it's by differentiating each one of these terms, term-wise differentiation, which can be written as, if I differentiate each one of those terms, I will get C1 plus 2C2 x minus a plus 3C3 x minus a the whole square, um, etc. Which is, this is the expanded version. If I write in a concise way in the sigma notation, it will become sigma n varying from 1 through infinity n c sub n x minus a to the power n minus 1. Then this is for the differentiation. So you can also integrate this f of x. So integration is also done term-wise. So if you integrate that, you're going to get constant of integration is going to appear. That is, let's say c. Then if I integrate each one of the terms, I'm going to get c0 x minus a, c1 x minus a the whole square over 2, then C2 x minus a the whole cube over 3, and so on. In the sigma notation, you can write constant of integration plus sigma n varying from 0 through infinity c sub n x minus a to the power n plus 1 over n plus 1. And also one more thing about this derived series and the integrated series. If the original function represented as a power series has a radius of convergence r, then the radius of convergence of the power series in equation 1 and 2 will also be r. So the radius of convergence for the power series for f prime x and for the integral, both of them are going to be r. This is another way of looking at it. Equation 1 and 2 in theorem 2 can be written in the form derivative of the power series or the function represented as a power series. So you can actually take each derivative of each term and then add and then use the sigma notation. So it is sigma of the derivative of each of the terms. That is what this is telling. Then same way, integral of the power series is power series with sigma inside. It is sigma of the integral. That is, you can take integral of each of the term and then add. Integral of the sum is sum of the integrals. Although theorem 2 says that the radius of convergence remains the same when a power series is differentiated or integrated, this does not mean that the interval of convergence remains the same. Very important information. The radius of convergence is the same for the function in the derived one and the integrated one, but interval of convergence is not the same. You are going to, it will differ at the endpoint. So you have to actually plug in the endpoints of the interval of convergence to see whether the series, the given function converges or not. It may happen that the original series converges at the endpoint, whereas the differentiated series diverges there. The idea of differentiating a power series term by term is the basis for solving differential equations. Now let's try an example based on this concept. Express 1 over 1 minus x square as a power series by differentiating Let's consider our familiar geometric function represented as a geometric series. So 1 over 1 minus x equal to 1 plus x square, etc. In the sigma form, which is equal to sigma x to the power n, where absolute x is less than 1. And then we are going to use the radius of convergence also. We are going to find the radius of convergence as well. But the hint given in the problem is by differentiating something, right? We are going to differentiate this equation 1 over 1 minus x. The second part of the question is find the radius of convergence. So let's start with the power series representation of the function. 1 over 1 minus x, the expanded form is 1 plus x plus x square, etc., which can be written in the sigma form as x to the power n varying from 0 through infinity. Now let's differentiate this. So derivative of 1 over 1 minus x, that is derivative of 1 minus x to the power negative 1. So chain rule is what you must use. Negative 1, 1 minus x to the power negative 2 times the inner derivative. Inner derivative is negative 1. So you get negative 1 times negative 1, positive 1, 1 over 1 minus x, the whole square. So if we differentiate both sides, you get 1 over 1 minus x, the whole square. You are differentiating this, so it is going to be 0 plus 1 plus 2x plus 3x square, etc. You differentiate the sigma, it is going to be n x to the n minus 1. Here it will start from 1. Because the first term is 1. That should agree with n equal to 1 here. So you can write this as sigma n times x to the power n minus 1, n varying from 1 through infinity. If we want to write this sigma, we want to write this 1 over 1 minus x square, starting from n equal to 0. So if you have to use 0, if you want to use that, what you are doing is actually pushing this value 1 to the left by 1 unit, right? So we are pushing 1, you're going from 1 to 0, you're moving backwards 1 unit. If you do that backwards 1 unit, you have to move this guy forward 1 unit. So n will become n plus 1. X to the power n minus 1 would become n. So if you notice, writing 1 over 1 minus x the whole square, either like this or like this, they are one and the same. One is starting with n equal to 1, the other one is starting with n equal to 0. The best way to make sure that what you're doing is right, so if you choose 0 through 1 through infinity, the very first one, n x to the n minus 1, you give successive values for n. So it will be 1 times x to the power 0, then 2 times x, 2 times x, then 3 times x square, etc. If you do n varying from 0 through infinity, n plus 1 times x to the n, you're going to get the same thing. You start with n equal to 0, that is 1, the first term, then n equal to 1, so that will be 2x. So you can verify that both represent the same function. So 1 over 1 minus x the whole square can be written as a power series like this. What is the radius of convergence? The question is also asking you of the radius of convergence. What is the radius of convergence? Radius of convergence for this one is exactly the radius of convergence of the original power series. The original power series is the geometric series here. So here it comes from absolute x less than 1. The radius of convergence of the original power series, original given series, is 1. Therefore, radius of convergence of the derived one is also r equal to 1. So I'll be continuing with a couple more problems in this video. So that will be done in part C of this section, part C of this concept video for section 11.9. Please watch part C as well.